So some things to get us started here, okay, with the dual nature of matter and radiation. First is the photoelectric effect. I'm going to read the definition. We have a slide for it coming up. But the photoelectric emission, sorry, or the photoelectric effect is this effect that if the right wavelength of light is shined onto some metal, electrons will be emitted from that surface. It might mean nothing right now, but it will hopefully in a moment. Photoconductive effect. Certain metal plates are better able to conduct electricity as long as light is striking them. Photovoltaic effect. Electrical voltage is generated between materials as long as light is striking them. If you use solar in your home, if you ever relied on a solar device at all, you're taking advantage of the photovoltaic effect. Light hits those materials and generates an electric current. Okay? So light can move electrons because electrons can absorb light. All of these effects are explained in Albert Einstein's paper in 1905 called the photoelectric effect. What else did Einstein do in 1905 that I was talking about earlier? Speed of light. He didn't figure out the speed of light. He figured out that it was a constant, and he wrote down all the ramifications for it, all the effects of it. Yeah. One of them was that everyone measures the same speed of light, right? And all these crazy consequences from that, all in 1905. 1905 was what was called Albert Einstein's miracle year, okay? He doesn't invent his theories of gravity till 1915, but 1905 he does all this amazing stuff. He later wins a Nobel Prize, interestingly not for relativity, which is what he's best known for. He wins his Nobel Prize for this, okay? The photoelectric effect, because it was the start of quantum theory, okay? This was the beginning. So Einstein figured out that when you shine light onto specific types of materials, they will emit electrons, one at a time, okay? Meaning that the electrons are having to absorb specific amounts of light, quanta of light, in order to gain enough energy to be emitted, to fly away from the material that they were originally in. An orbiting electron can absorb all of the energy or light, all of the energy from a light photon. We call these light photons quanta. A single one is a quantum. Many of them are many quanta. And when it does that, the electron gets ejected from the atom. It sounds like you're saying that the photoelectron absorbs one piece of light, one particle of light, and then goes flying out of the atom that it was a part of, okay? So, in this way of talking, the light's a particle, okay? The light is absorbed one piece at a time. Particles come in pieces, right? A wave does not come in pieces. A wave is kind of a big spread out thing, right? This was easiest to explain if the light or X-ray photon is visualized as a quantum, a piece, or a packet or bundle of energy. So that was the picture that Einstein liked. He found this to be the best explanation of the photoelectric effect, that light was absorbed by these electrons, one piece of light at a time, okay? The opposite should be true then too, right? If electrons can absorb light one piece at a time, then they can emit light one piece at a time, okay? So this sounds suspiciously like particles. So, is light a wave or is it a particle? We've said it's a wave a bunch of times, right? It's an electromagnetic wave, but then Einstein in 1905 tells us light acts like a particle. It absorbs one piece at a time, like particles do, okay? So on the other hand, Einstein says particle, but on the other hand, experiments come along, such as the double slit experiment. The double slit experiment is interesting. So I'm going to actually show you this thing here is a small version of the double slit experiment, and I'll show you in a second here. Here's the idea. Waves can interfere with each other, okay? If two water waves, ignore the picture for a second. If two water waves come together, right? And you ever been in the ocean, had two waves cross over each other? It makes like a wave twice the height, and then you get swamped by that one big wave, right? So if two positive waves come together and hit each other, it makes a wave double the height, okay? If a positive and a negative wave come together, they deconstructively interfere and cancel out, okay? Positive waves interfere constructively, making a bigger wave. Positive and negative waves interfere destructively, making no wave. Okay? So we have this property that waves can interfere with each other. Okay? If I took a source of light and I emitted it one photon at a time, turn on one photon at a time, and I send it through, ignore all these wave pictures for a second, just pay attention to this here. If I took a light emitter, like a flashlight, a special one that I can control one photon at a time, okay? If I send it at this double slit opening, one particle at a time will either pass through the left slit or the right slit, yeah? If it were like a ball, right? I make two slits to pass through and I throw the ball, it's either gonna pass through the left slit or the right slit. Ignore the fact that it could bounce off of any of these other things, but assuming it's going to pass through something, it's either going to pass through the left or the right, yeah? And then I put a detector on this side, okay? And my detector tells me that it either passed through the left slit or the right slit, and it's going to make a little dot on the left side or the right side as the ball hits the detector, okay? We know that as many times we throw this one ball at a time, it will either hit the left side or the right side of the detector, making a blotch on the right side or the left side. Okay, that's what works for balls. When you do this with light, turn a flashlight on, for example, the light waves spread out. So ignore the single photon thing for a second. The light waves spread out. A single wave of light will spread out, traveling through both slits, like a water wave would. Okay, you can imagine doing this in the ocean with water waves. Like make a wave in the water, watch that wave travel through, and it can go through either this slit or this slit. The wave goes through both, okay? Splitting it into two waves. Those two waves can then constructively or destructively interfere. When those two waves run into each other and they're positive waves, they'll make a big wave. When those two waves run into each other and they're positive and negative, they will destructively interfere and make a negative wave. So over on a detector, you would get this interference pattern. Spots where the waves were constructively interfering, making big waves. And in between those two spots are these openings where a positive and a negative wave come together and make nothing. Okay, they destructively interfere. Okay, so waves can interfere with each other. When this dual slit experiment is done with light, we see an interference pattern. We see stripes of positive wave, negative wave, positive wave, negative wave. Okay, that's when light, a big source of light, is shining through these double slits. Interestingly, even when this is done a single photon at a time, it still builds up an interference pattern. Okay, so let me show you the dual slit experiment with this little laser. If you wanted to do this at home, it's going to be very difficult to do if you don't have a laser. Like visible light spreads out too much. You need a laser light to make this work. But I have to make it very dark in here. All right, so bear with me when we get very dark. Okay. Very dark now.
Oh, good.
All right, now we can relax, right? Okay. All right, this takes a second to set up. I can't see anything. All right, let's see. Let's put this in the right spot. Okay. So let me first, that's showing you the interference patterns. I'll go up and talk about that in a second. But just consider the laser being pointed at the wall right now, right? It's more or less a single dot, yeah? There's a little bit of, see the scattering around the laser?
Yeah.
All those green speckles, that's scatter. Because the whiteboard's not an even surface. It's not a flat surface by any means, according to the laser light. I mean, it seems flat to us, but it's just not. So it's a single dot, though, roughly. And then I take that dot, and I pass it through a teensy little slit that I made with electrical wires. Okay? And what you should hopefully see here is that there's a bright spot in the center, right? Yeah. That gives us our center. That's where the light was, that's where the main source of light is pointing. But then do you see how it goes bright, dark, bright, dark, bright, dark, moving away to the left and the right of the middle of the source? Those bright spots, so remember that laser light, which was one single dot, is now passing through two slits, yeah? So that's taking the wave and splitting it up into two separate waves. Those two separate waves travel forward from the slit forward separately, and they spread out separately, okay? Those two separate waves now are going to start hitting each other. Where those two waves hit each other and constructively interfere, that makes a green dot. So you see all these green dots, right? Where the waves destructively interfere and cancel each other out, we get these black lines, okay? So this shows us that light is a wave. It has to behave like a wave. It has to be a wave because it behaves like a wave. Waves exhibit interference patterns as they pass through a dual slit test, okay? So this test proves, it should prove at least, that light, visible light, all types of light, are waves. We see these interference patterns being made as it travels through that dual slit. So, there's the light back on. So Einstein tells us light's a particle. Other tests confirm light is in fact a wave. So then we gotta go, well then what is it? Right? Is light a wave or a particle? Now that you know what you know, what do you think? Wave or particle? What do you think? A wave? All right, light's a wave. How do you account for the fact that it's emitted one at a time or absorbed one at a time, like a particle?
They both have argument to be either one.
Absolutely.
Yeah.
So there's no good answer. They are both. Okay. So let's read on. You guys are doing great. So numerous experiments have shown that X-rays and all other forms of light are waves, Sergio's right, that act like particles in the right circumstances, such as when they're being absorbed or emitted. Okay, they're emitted one at a time, absorbed one at a time, like particles are. Okay, so here's the trick. They're absorbed like particles, but they travel like waves. Okay, so as they're moving through space, they're a wave, but absorbed one at a time like particles are. Okay. In fact, it goes even deeper than that. Particles are not particles. The particles that we were talking about, electrons, protons, neutrons, are not particles. They are waves, okay? A French physicist, Louis de Broglie, wondered that if subatomic particles like electrons, because they could have done this back then, they wondered if electrons were kind of behaved like that too. And so he shows some fancy math that says, yeah, electrons should behave like waves. Okay, he explained the wave-like behavior of electrons. And then they did experiments. They did the dual slit experiments with electrons instead of light. Okay, and you can actually control the emission of electrons to get it down to one single electron at a time. Again, if this were a dual slit experiment, hang on, pause.